Hi, students. In this video, we're going to talk about energy. And a lot of people wonder, well, why are we talking about energy in chemistry? What we have to understand is chemistry is a study of matter, but energy affects matter, and matter affects energy, really. So an example is, okay, we study combustion reactions. What we have to realize is what accompanies a lot of reactions is a change in energy, right? So I don't burn wood in a fireplace because I like all the ash and smut, right? Why do I burn wood? I burn wood because it releases energy in the form of heat. That heat keeps me warm. So when the wood's burning in the fireplace, I'm warm. So we have to study energy because with chemical changes, energy can be released or absorbed. So energy is anything that has the capacity to do work. When you have a lot of energy, you can do a lot of work. You go to the gym, you get a lot of exercise done. You're all pumped up. Maybe you get your studying done. That's energy, right? So what exactly is work? Well, work is force over distance. Okay, so and force, right, is mass times acceleration. Now, we don't need to know physics, okay, but for anybody who's taken physics in this chemistry course, it doesn't hurt at all. So here's this guy, right? He has a box in front of him, right? This box has a certain mass, and we can say kilograms, right? So force is mass times acceleration. For this to move, the acceleration, right, is typically meters per second squared, okay? So acceleration is meters per second squared. Now, for chem, again, you don't need to totally know this, but I want to bring that to the table for you guys to relate it. Now, for him to complete the work and make this force work, he has to move it a certain distance. And that distance measured in meters. So he's doing work on this system by doing what? Moving it. How is he moving? He's doing work. He's using up energy, right? So the units end up becoming kilogram meters squared per second squared. And we'll see that when we talk about kinetic energy in the next slide. So just like in the system, right? So this box I can call the system. The man is the surroundings, and he is working on the system. So the work is coming from the surroundings. It's a flow of energy. It's a flow from this man, the surroundings, onto this box, the system, and it's flowing. Well, another form of energy that we must talk about, just like the example that I brought up with combustion, is the flow of heat. And the flow of heat energy or thermal energy is caused by a difference in temperature. So if something hot touches something cold, the heat from the hot is going to flow to the cold, right? That's why if you touch a hot frying pan, you'll get burned because there's a flow of heat, energy to your hand. So we have to understand that energy can be exchanged between objects. How? Through contact. So I showed that example here. The box is a system. The man is the surroundings. It contacts the system, and through using work, energy, the energy flows into the system, and it's able to travel a certain distance. Heat flows from hot to cold. Another thing, well, collisions. When things collide, kinetic energy can flow. We see that in football or in many things. A classic example is with kinetic energy. So kinetic energy, sometimes shorthand KE, is 1/2 mass times velocity squared. Now, again, this isn't exactly, a physics course, but it's nice to have some basic understanding. Think of kinetic energy as movement. As particles move faster, they have more kinetic energy. What are the units of kinetic energy? Well, the mass is kilograms, and the velocity, right? Velocity is a rate, it's speed. So like miles per hour, right? But typically, because we're using the metric system, Instead of miles per hour, it's meters per second. And if I square that, I get kilogram meter squared per second squared. And that unit is a joule. And that's how we measure energy in chem. We use joules. And joules are just kilograms meter squared per second squared. We saw that in the previous with the work, right? Remember, work was force times distance, which really is a Newton meter, but we showed that the force was mass times acceleration on that last one, and right, mass times acceleration times the distance makes you mad. No, I'm joking. It's these units, kilograms per meter squared per second squared. So here I have an example, and I'll erase this, of kinetic energy. And I see that there's a transfer of energy due to a collision. So if I look at this billiard ball, right, once I hit it, it's moving, right? So it has a mass, it has certain kilograms, and now it's moving at a certain velocity. So that motion is what we call kinetic energy. It can transfer that energy based on a collision, do some work, so that's a form of energy, and now once it does work by hitting this ball and transferring its energy, now this ball has absorbed that kinetic energy and it moves. So I had said earlier that thermal energy is the energy associated with temperature, right? So you can think of heat, right? Thermal energy as a form of kinetic energy. The big difference is when we look at the macro world, like billiard balls, right? Or people running, we think kinetic energy, motion. So you could think of heat energy at a microscopic level, at an atomic or chemical level. When particles move faster, they have more heat, and that heat can be transferred, right? So another example is if you rub your two hands together really fast, as you move faster, right, your hands get hotter. Well, it's the same thing. Kinetic energy. As the billiard ball moves faster, it has more kinetic energy. Heat or thermal energy. As the particles move faster, they have more heat, more energy, and they can transfer that energy to coolers systems. So what about potential energy? Potential energy is another big one. The two things that we talk about a lot in this class is kinetic and potential energy and different forms. Potential energy is the energy stored in a system, okay? So you can think of, well, here I have the billiard ball, right? And it has energy stored. How come? Well, the billiard ball wants to fall because of gravity, okay? And it has an attractive force to the earth. Okay, it falls down because the earth is bigger. The earth's not going to fall to the ball, right? The earth is bigger, so the gravitational force in the pull goes down. But where the stored energy is, it comes from this distance. So this distance right here is stored energy. And as you release the ball, some of that potential energy, right? So from here, I had this much distance. If I look over here on this slide, now half of that distance has been converted to kinetic energy when I let go. And then I still have this much potential energy in this frame, but we'll see as more of the potential energy is transformed to kinetic, it'll eventually hit the ground and there will be no more potential energy because there's no more of a distance. So potential energy, again, if you've taken physics, this helps. Potential energy is mass times gravity times the height. So the mass of the object, kilograms, right? Gravity, acceleration, meters per second squared, right? 9.8. And then the distance is in meters. And what do we end up getting? We end up getting the same thing that we did for the 1/2 mv squared, the units of kilogram meter squared per second squared, which is a joule, just like we did for work in that very first slide. So all the forms of energy equal 1 joule. So you have to understand potential energy is basically stored energy. That's what dams are built for. They hold back the water and store their energy because water likes to flow downhill. And when you let it go through a small opening, that water can rotate an electrical turbine and produce electrical energy. So energy is stored basically based on distance, right? Well, if we think of atoms, okay, when you think of an atom, what do you have? You have a nucleus, and then you have these orbits with electrons certain distances from the nucleus that has protons. Well, guess what that distance is? Potential energy, right? As the electron is further away, as this distance gets further, there's more potential energy stored in that electron because it wants to get to the nucleus. So the structure of an atom is basically potential energy because there's a distance between attractive forces, protons and electrons. Now, the reason why we talk about potential and kinetic energy is the law of conservation of energy. We can't create or destroy energy, we can only transform. So I can take this that has a great distance, right? I have a height and I have a mass and I have gravity pulling on this. So this is a ton of potential energy. Once I throw this over, it's going to transform to motion, kinetic energy, and some of that motion, when it lands on the ground, will be transferred at a molecular level as heat. So I didn't create or destroy energy, I just transformed it. I took something with potential energy, pushed it over, created kinetic energy, and some of that kinetic energy was also released in the form of heat. So that's what you need to know. We can transfer energy from one object to another. So what are some forms of energy? Electrical energy. Why? Well, the flow of electric charge, right? When we think of a circuit, you have electrons going through a circuit. That's why old copper wiring, right? Why do we use metals and copper? They conduct electricity. They lose their valence electrons and they pass them through a circuit. That creates an electrical current. Heat is a form of kinetic energy. Molecules moving faster. Light, right? Transitions through space, kinetic energy. But there's also potential energy. Potential energy is in the nucleus. An unstable nucleus has a lot of potential to release energy, right, in the form of some type of nuclear radiation. So alpha, beta, gamma. But really what's important is what I like to call, everyone refers to chemical energy. Chemical energy is basically potential energy at a molecular level. Just like heat is kinetic energy at a molecular level, chemical energy is really just potential energy. And why is that? If you look at atoms, right, based on the position of the electrons, based on the position of the molecules relative to each other, that is potential energy. And there's changes in the potential energy based on how the atoms align with each other. Now, why is that important? Remember, energy has a capacity to do work. Right? There's two types of energy that we've been discussing: kinetic, potential. Kinetic is due to motion. So when we think about chemistry, when we're studying matter and chemical changes in matter, kinetic energy, we're thinking thermal energy. We're thinking changes in temperature because of heat transfer, right? The movement of particles transferring heat. So that's why we talk about kinetic energy, because we're thinking of heat. Now, why do we talk so much about potential energy? Well, that's energy based on position. Well, the position of the atoms in a molecule, right, influence its amount of energy. And as reactions occur and, you know, reactants bonds break, and to make new products, you know, we have to make new bonds. Well, now I have new position of atoms. And that's what we call chemical energy. And if you've taken bio and you've learned about cellular respiration, what do? We consume glucose to form ATP. Well, what do we mean by ATP? ATP is stored chemical energy. Why? There's new positions in those bonds, in the phosphate bonds, that allow us to release energy in the future. So that's our kind of discussion on energy. This video was a little bit longer than I thought. I apologize, but I hope you enjoyed it. I hope it made sense. And thanks for watching.